Okay, so we're going to look at modeling exponential functions. So one kind of exponential function problem that you might see looks at doubling time. So doubling time is the amount of time it takes for a sample or population or etc. to be increased by 100%. So it's going to increase by the same amount that you already had. Okay? Or in other words, it's the amount of time it takes for it to double. So earlier when we looked at the warm-up, we looked at a bacteria in a petri dish, and we were told that the bacteria doubles every 3 hours. So this amount of time here, which is 3 hours, represents your doubling time. Now we're going to look at the problem again, and this time instead of using a table to come up with the solution to the problem, we're actually going to do the question by coming up with an equation. So here's the first example we're going to be looking at. Okay, so example 1, the number of bacteria in a petri dish doubles every 3 hours. Surprise, surprise. If the initial population is 36, A, determine the equation that models the population of the bacteria after T hours. So let's come up with an equation. Now, I know the general equation that represents exponential growth or decay is y equals A times b to the exponent x. Okay, and maybe I'll put the b in brackets just so I don't accidentally try to multiply the a and the b together. So I'll rewrite it like this, y equals a times b to the exponent x. And so now I'm going to introduce some variables that are actually represented in the problem I'm looking at. So my dependent variable looks at population, and my independent variable is looking at time, which is already highlighted there. So I'm going to rewrite my equation based on population and time. So I'm going to write P of t, the population over time, is equal to, A represents my initial population, which I'm given in this case is 36. And B represents your exponential growth or decay ratio. Now, because I know that the bacteria is going to double every 3 hours, I know that this is going to change to a base of 2. Okay, I have to multiply by 2 each time to get the next population amount. Now, if I leave the exponent as just t, what this means is every hour the population is doubling. But that's actually not what's happening. What's actually happening is that every 3 hours the population is doubling. So I need to show that in my equation. So t on its own means that it's happening every hour. T divided by 3 means every 3 hours the population is going to double. So this is my, oops, went right through it. So let me just rewrite that. I made a mess. No worries. So I just rewrite what I had just written. So I had y equals a times b to the exponent x. And my dependent variable is population over time. My initial population was 36. My growth ratio is 2 because it's doubling. And the amount of time it takes to double is 3 hours. So instead of just writing t as my exponent, which means every hour, I'm writing t over 3, which means every 3 hours. So this is my equation that I'm going to be looking at. There we go. Okay, part B says determine the population of the bacteria after 12 hours. So we're looking at the same problem as we did in the warm-up, but now we're going to use the equation instead. So after 12 hours means that t is equal to 12. So I'm going to look at the population at a time of 12 hours. And I get 36 times 2 to the exponent 12 over 3. So I replace t with 12. And I get P of 12 equals 36 times 2 to the exponent 4. Which if I use my calculator and simplify, I get P of 12 is equal to 576. Just like we got in the warm-up. Okay? So therefore, the population after 12 hours is 576 bacteria. Okay, so we can actually take this formula formula here, and we can actually simplify it for any general population growth which is being doubled, so any doubling time problem. And here's a summary of what the equation would look like. Now, I don't want you to memorize this because all your equations can be rederived from the general equation of exponential growth or decay, which is y equals a times b to the exponent x. So please don't memorize this. This is just another way of seeing it. What do each of these variables mean? Well, P of t represents the population over time. P naught, so there's a little subscript of 0 here. P naught represents the initial population. T in the exponent represents the amount of time you're actually looking at in the problem. D in the denominator of the exponent represents the doubling time, so how long it takes for it to double. But what I do want you to remember is that your time value and your doubling time value must have the same unit. So they either both have to be in hours, both have to be in minutes, both have to be in years or seconds. Both of them have to have the same unit of measure.